In this video, we're going to go through the topic of vectors. And let's start by defining a vector. So a vector is a quantity that has both magnitude and direction. So magnitude is size or length, and we are already familiar with a quantity that has magnitude only, which is a scalar quantity. So a scalar quantity has magnitude only, all right? An example of scalar quantities are all real numbers. So 7 or 11.12 or 10, 12, and so on. Now that we're getting familiar with vector quantities, let's look at how we can represent them. So vectors are often represented as arrows, okay? So the anatomy of the arrow. We have the tail and the head. So the length of the arrow represents the magnitude. So this represents the magnitude, which is the size or the length. And the head of the arrow, which is where the vector points, represents the direction. And there are some vector quantities that we are already familiar with, such as velocity, force, weight, and momentum. And there are many others, and these are called vector quantities because they have both a magnitude and a direction. So now let's look at notation of vectors. Notation of vectors is how we would represent vectors on our exam, or how we could recognize these vectors. So let's say we have a bold v, right? A bold lowercase v. We could differentiate this bold v from a not bold v and know that the bold v would be a vector quantity and the one that isn't bold would be a scalar quantity. So we can use these like a bold or an arrow over a particular letter to say that this is a vector quantity, and without would be a scalar quantity. So this distinguishes them from scalar quantities, okay? And I would recommend when you are using vectors, like when you're going to write your vector, you put an arrow over it, because what may look bold to you may not look so bold to someone else, okay? So it is subjective. So put your arrow over it, it's just easier. Now, for the purposes of this video and for CAPE, we are going to be looking at vectors in 2-dimensional space as well as 3-dimensional space, putting a stress on the 3-dimensional space because you may be familiar with 2D already, but we're gonna go through that as well. So vectors in 2-dimensional space has the x-axis and the y-axis, and 3-dimensional space has 3 axes, x, y, and z. So there are 2 main forms in which we're going to see vectors and be able to have to write the vectors in these forms as well. So this will be component form and unit vector form, okay? Component form has 2 dimensions as well as 3 dimensions. We can write them in both. So can unit vector form. And they are actually equivalent to each other in the sense that we can exchange between them. We need to learn that. So for 2 dimensions, component form, we have x and y in a column within brackets. And for 3 dimensions, remember, we have 3 values. So x, y, and z in this column within brackets, okay? Where x, y, and z are the relevant entries of the vector. Now for unit vector form, a vector can be expressed in terms of the unit vectors I, j, and k in 3D space. And if we had 2D space, we would have I and j, all right? So for 2 dimensions, we have xi, so xi and yj. And for 3 dimensions, we have xi plus yj plus zk. This would be the 3rd dimension, right? So what exactly is I, j, and k? These are called unit vectors, which we will go through in a couple minutes. But for now, just note that in 3D and 2D spaces, well, we only have, for 2D spaces, I and j, because in 3D space, we have 3, remember? And in 2D space, we only have 2. So we have I and j. And for 3D, we have I, j, and k. So I would be 1, and then no values, because these, remember, this would be j, this would be k. So here we have 0, 1, 0 for j. And k, we have 0, 0, 1 in the 3D space, right? So we'll get into that more in a little while. But for now, just try to familiarize yourself with these forms, because this is what we're going to have to know. So let's go through the fundamental operations of vectors. We are already familiar with how to add, subtract, and multiply scalars because we do it all the time. However, do we know how to do those same things for vectors? The answer is we will. So let's get into it. The first fundamental operation that we're going to learn about is how to add vectors. So the addition of vectors. Why would we want to add vectors together? To obtain other vectors. And how do we do it? Well, that's a good question. We can add vectors by adding their corresponding components. So if we look at the vectors A and B, we can see we have A1, A2, A3, B1, B2, B3. And when we put them next to each other, we can line them up, right? So we have to add A1 and B1, A2 and B2, A3 and B3. So when we add those, we get our answer. That's how you add vectors in component form. However, with the unit vector form, you can see we have I, J, and K for both A and B, right? So what we're going to do is look at the coefficients of I, add them together, the coefficients of J, add them together, and the coefficients of K, and add them together. And that's how you add the vectors together. So we add these and we're going to get our resulting vector. So let's look at this example. We have A and B. A is 1, 2, 3, and B is 3, 2, 1. What we're going to do is write them next to each other, put the add and the addition sign, and then we are going to look at the corresponding components. Then we're going to add them together. It's very simple. So 3 plus 1 is 4. 2 plus 2 is 4. 3 plus 1 is also 4. So the answer to this question is 4, 4, 4. And how can we write this in the unit vector form? We would have 4i plus 4j plus 4k. All right? So that's how we add vectors. Now we know how to add. We need to learn how to subtract them. So we could subtract vectors to obtain other vectors, just like how we could add them. How do we do it? The exact same way. So we are going to subtract the corresponding components. So A minus B would be A1 minus B1, A2 minus B2, and so forth. And the same for this one. Remember, we have I, J, and K, our unit vectors. And then we're going to subtract A1 minus B1, A2 minus B2, A3 minus B3, and then of course we have our I, J, and K. Now let's look at an example. We have A as 1, 2, 3, B is 3, 2, 1. The only thing you need to be mindful of is the signs. And of course, we're going to have 1 minus 3 is minus 2. 2 minus 2 is 0. And 3 minus 1 is 2. Okay? And if we wanted to write this in the unit form, we can have minus 2i. We do not have a j, so we just leave that out, and we have plus 2k. And that's the answer. Now we are going to learn how to multiply a vector by a scalar quantity. So we can multiply a vector by a scalar quantity in order to obtain another vector in the same or opposite direction, which depends on the sign of the scalar quantity. So a negative scalar would result in a direction flip. So how are we going to multiply? Don't know why we have missing letters here, but this is vector by a scalar quantity. We can multiply a vector by a scalar quantity by multiplying their corresponding components by the same scalar quantity. So let lambda be any scalar quantity. Let's look at this example. We're going to multiply lambda by the vector A. So remember, A is A1, A2, A3. All we're going to do is multiply that same scalar by all of the components in this vector. So we're going to have lambda A1, lambda A2, lambda A3, and the same goes for this, right? So we're going to have lambda, it's the exact same thing, but instead in this form. So we have the I, J, and K. All right, so let's look at an example. We have lambda to be 2, which is the scalar quantity. And then the vector is A, 1, 2, 3. So all we have to do to get lambda A is, we could put 2. This is how we write it. So we have 2, 1, 2, 3. And then we're going to multiply it like this. 2 by 1 is 2. 2 by 2 is 4. 2 by 3 is 6. And this is the answer. Remember, this could also be written as 2i plus 4j plus 6k. Okay? And that's how we multiply a vector by a scalar. And finally, we're going to learn about the equality of vectors property. So we know that two vectors would be equal to each other if their corresponding components are equal. So they are equal if they have the same magnitude and direction. Okay, so we're going to say that these two vectors would be equal to each other if and only if a1 is equal to b1, a2 is equal to b2, and a3 is equal to b3. They would only be equal if those corresponding components are equal to each other. And similarly, with this form, a1 has to be equal to b1, a2 has to be equal to b2, and a3 has to be equal to b3. And what can we take from this? We can look at this example. So we can say that if a question says that a1, a2, a3, this vector is equal to this, we know that a1 would be equal to 1, this would be the value, a2 would be 2, and a3 is 3. It's a simple thing, but sometimes, we just need to go through these simple things. So now that we've gone through the fundamentals, we can now move on to slightly more complex concepts, even though they're not actually complex, I just saying. They're a little more difficult, because those were very easy, as you would have seen. So the magnitude of a vector, let's begin. The magnitude of a vector is also known as the length of a vector. So if we wanted to find the magnitude of a vector, the length of a vector, let's say in a 3D space, we have this vector, A is A1, A2, A3, then this would be the formula. So this is the notation for the magnitude, and this would be the formula. So you just plug in the components here. And for a 2D space, if we have this vector and A1, A2 being the components, then we just plug them into this formula here, and we would find the length of that vector A in this example. So let's actually look at an example, and it states to find the magnitude of the vector 3i plus 4j. So 3i plus 4j, and we have the notation, would be equal to, and then remember, all we're doing is plugging it into the formula. Plug it into your brain or your calculator, whichever one you trust more. And then you would get the root of 25, which would be equal to 5 units. And that would be the magnitude of the vector 3i plus 4j. Okay? Now we're going to learn about position vectors. And this is where it gets a little more serious. So position vectors usually start at the origin and can be used to determine the location of one object with respect to another. If we have a point P, then the position vector of P starts its tail at the origin and ends with the head at the point P. Okay, now let's go through that. So remember, we have a point P, all right? The position vector would be denoted by OP, and then we would have the arrow on top, right? So this is the notation, OP, it could be OA if the point was A, anything like that. The position vector means that it will start at the origin, so this is 0 here, and then we go all the way up to point P. And since we have a point here in this example, we have a point P, which is 3, 4, we could plot that point, and the position vector would be this arrow here, okay? So we will say OP in this two-dimensional space is equal to 3, 4, and that's how we write the position vector, all right? So let's look at this question. If we have a point R, which is minus 1, 1, what is the position vector? So remember, the notation for the position vector would be OR with an arrow on top, and you actually don't have to draw anything. It is very simple. All you have to do is write it in this notation instead. Minus 1, 1, this vector notation, right? So this is the answer for the position vector of this point R, minus 1, 1. But this is just a demonstration of what it actually looks like. Now, on to displacement vectors. So displacement vectors use position vectors in order to obtain vectors which do not start at the origin. So remember, we had it starting at the origin now. Now it could be randomly placed. So let's just say we have these dimensions, and this is the vector now. And we actually don't start at the origin, so how are we going to find it? This is where we could use displacement vectors, use position vectors to be able to find it, okay? So if we have 2 points, P and Q, with their position vectors being OP and OQ respectively, we can obtain the vector PQ by using this rule, okay? So PQ, we could find this by using the position vectors of P and Q. So PQ, it goes like this, is equal to OQ minus, and remember this is a minus, not a plus, OP. So these position vectors, right? And what you need to notice is that the last guy, like the second letter, comes first, okay? So let's say we have AB. We can find AB by using the position vector OB minus OA. This second guy comes in first, and you subtract it from the initial first guy here. So they switch in places, and then you subtract it, okay? Make sure to remember that and don't mix it up, because this is going to be used. It's very important, okay? So let's look at this example. We have 2 points, P and Q, where we have P is 1, 1, and Q is 2, 1. So OP, the position vector, would be 1, 1, and OQ would be 2, 1. If we wanted to find PQ, we could use the formula OQ minus OP, and of course we use exactly what we learned before, how to subtract vectors. So the corresponding components, 2 minus 1 is 1, 1 minus 1 is 0, and we could also find QP. So QP, remember, this will come first here, so OP minus OQ, and that's how you find it, okay? So then we plug it in, subtract to get the answer, minus 1, 0. All right, and that is QP, and this was PQ, okay? That's how you use displacement vectors. Now, this question, find BA given OA is this, so this is a three-dimensional one, a three-dimensional vector, and OB, this position vector, is 4, 1, 3. So now we know that BA would be equal to OA minus OB, these position vectors. Then we would have, well, I actually have it right here. So we have 3, 5, 6 minus 4, 1, 3. 3 minus 4 minus 1. 5 minus 1, 4. 6 minus 3 is 3. We subtract the vectors by subtracting corresponding components, and that's how you solve it. And now on to unit vectors, which is what we touched on a little bit earlier with the special unit vectors I, J, and K, but as promised, we're going to go through it in detail now. So remember, I always keep my promises. Okay, so unit vectors. As the name suggests, are vectors with a magnitude of 1 or a unit magnitude. So unit 1. So a unit vector of a vector, any vector, let's just say in this case A, is given by that vector over the magnitude of the vector, right? So the unit vector A is given by A over the magnitude of A. This makes sense as we are taking the vector and dividing it by its magnitude so that the outcome is a vector with a unit magnitude. And we have to take note that the direction of the original vector is preserved in the unit vector. So let's look at this example. Let's find the unit vector of A. So A in this example is 3, 4, which is a 2D vector, right? So we have to find the unit vector. So to do that, we need A over the magnitude, right? We have A, we need to find A's magnitude. To do that, we plug it into the equation which we learned earlier, simplify it. So we have 9 plus 16, and we have to square that. We get 5. Hence, the unit vector of A will be A over 5, and then we get 3 over 5 and 4 over 5. Now, is the magnitude 1? Okay? We have to check that to be able to know if it's correct, if the magnitude of this is 1. Okay? So if the magnitude is 1, congrats, you did it right. If it's not, you did something wrong, do it over. Okay? So we have to check if the magnitude of our answer, if the magnitude of our unit vector is 1, we did something right. So we checked it and the answer is 1, so this is correct. This is in fact the unit vector. Okay? Now, special unit vectors, which is what we had in the beginning. So unit vectors in the direction of x, y, and z axes respectively are I, j, and k. And remember, we have I being the first one, j being the second, and k being the third component, right? So note that this is xi plus yj plus zk. Okay, so we went through that already. The next thing that we're going to learn is the scalar or dot product of two vectors. So let's say we have A and B, these two vectors, and we wanted to find the scalar or dot product of A and B. This is what we would do. We would multiply A1 and B1, add them to the product of A2 and B2, as well as the product of A3 and B3. We add these products together, and then we would get a number. And I was thinking, right, why is it called scalar product? It's because we get a scalar. This is not a factual. I just have a theory, okay? Because I was thinking, why is it called scalar or dot product? I was thinking the dot is because the notation is a dot. This could be wrong, y'all. This is not factual information. This is a dot, so hence the dot. The product, because we were multiplying stuff. And then scalar is because we get a scalar at the end. Anyways, that was just me thinking a lot. Anyways, let's look at an example. So the example states, the scalar product between the vectors 251 and 414 is, remember what we're doing, 2 multiplied by 4 plus 5 multiplied by 1 plus 1 multiplied by 4. We simplify it to get 17, which is a scalar. Okay. So the angle between two vectors, how do we find it? Now, this is very simple and yet so complicated because we need to find the dot product on top here and then the magnitude here. And we know those are really big formulas, right? So I suggest you do these in parts and then add them, then put them together and then find the result, okay? That's just my advice. If you don't want to take my advice, that's on you. Okay, so if we have two vectors A and B and we wanted to find the angle between them, the angle would be given as such: cos theta. So this is the angle you wanted to solve for cos, and remember when you find theta, it would be cos inverse of dot B over, remember that, okay? So theta would be equal to this. So that's the angle there, okay? So remember, when you're doing this, please take your time. It might mess you up. I wouldn't say will. Will is for me. It will mess me up, but it might mess you up. I don't know if it will. I hope it doesn't, y'all. Anyways, the angle between these vectors, 251 and 414 is, then we put this huge thing. I'm telling you again, don't rush it. It is easy to make calculation errors. Don't rush it. So you basically find a dot product on top here, and then the magnitude of these, and then you put them all together. We would get this, and then we have cos theta is equal to this after we simplified it, and then, as I told you before, theta is equal to the cos inverse of 17 over the square root of 990. Plug it in your calculator. I know you trust your brain. Plug it in your calculator. And then you get 57.3 degrees to be the angle between these two vectors, and that's the solution, y'all. Now, perpendicular vectors. How do we know if two vectors are perpendicular? Two vectors are perpendicular if and only if y'all would see people writing it like that, two F's, if and only if A dot B is equal to 0. So if the scalar product of these vectors is equal to 0, you know that these two vectors would be perpendicular to each other, okay? So the vector I plus j plus k is perpendicular to 2i minus 2k, to this vector, right? What can you tell from that information? We can tell that the dot product or the scalar product is 0 because it is stated that the vectors are perpendicular. So what we could say is that these 2, the dot product is equal to 0. And I'm just proving it in this case because you could basically jump from this to this. You don't have to go through all these steps. I'm just showing you that it's a fact. Okay, y'all? So we don't necessarily have to go to work it out because we already know that the dot product is 0 because of this special word perpendicular. So now we know about perpendicular vectors. What about parallel vectors? How do we know if two vectors are parallel to each other? Two vectors are parallel if and only if these two vectors are scalar multiples of each other. So scalar multiples implies that these two vectors are different due to the factor of a constant. So for instance, if we have vectors A and B such that A is equal to A1, A2, A3, and that is also equal to 3B1, 3B2, and 3B3, and we just had to take out that 3, and then they would be equal, we know that they would be parallel to each other. So let's look at this example. We have 4, 4, 8 and 1, 1, 2, and all we had to do was take out the 4. And so basically what I'm saying is if you multiplied all of these by 4, you would get 4, 4, 8, right? So therefore, we know that these two vectors are parallel to each other. 4, 4, 8 is parallel to 1, 1, 2. Remember, because they are scalar multiples of each other, okay? And therefore, they are parallel. And now we're going to move on to another part of the video, and we're going to focus on lines. So we're going to begin with the equation of a line, and there are two ways to find the equation of a line. The first way being with a point on the line and a vector parallel to the line, and the second being with just 2 points on the line. So let's focus on the first way, finding the equation of a line with a point on the line and a vector parallel to the line. So note that this is called the direction vector of the line because it gives us the direction of that line, okay? So the equation of the line in this case would be r is equal to p plus lambda m, and lambda would be all real numbers, where p is a point on the line, remember we're given a point, and m would be a vector parallel to the line because we're given that, and then r would be the vector that represents any point on the line, x, y, z. Okay, so now the second way is to find the equation of a line with 2 points on that line. So if we have 2 points A and B and their position vectors are OA and OB respectively, the equation of a line would be r is equal to OA plus lambda, OB minus OA, okay? And lambda would be real numbers. Now, the question. Let's look at this question. The question states to find the equation of the line passing through the points 1, 2, 3 and 2, 4, 6. So we already know that the equation of the line given 2 points is as such. So OA is 1, 2, 3, OB is 2, 4, 6, and all we're going to do is firstly find this, then plug it in, and we already know what OA is, and that's how simple it is. Okay, so we have the equation of the line to be r is equal to 1, 2, 3 plus lambda 1, 2, 3. Okay, so that's how you solve that question. Now we're going to look at forms of the equation of a line. There are 3 forms that we're going to look at: the vector equation, the parametric equation, as well as the Cartesian equation of a line. The vector equation of a line is as such. We have a fixed point on the line, so in this case we'll say A1, A2, A3, as well as the vector parallel to the line, okay? So this would be the direction vector. Then we have to note that this is similar to the equation of a line in the coordinate space y is equal to mx plus c, all right? So you notice that. Then we have the parametric equation of a line. We consider the vector equation to derive this, okay? So we get, if we replace r with x, y, z, we can get this. And if we simplify it, we get a1 plus lambda m1, a2 plus lambda m2, a3 plus lambda m3. And when we equate the corresponding components, remember how we do that, just like that, we get x is equal to a1 plus lambda m1, y is equal to a2 plus lambda m2, and z is equal to a3 plus lambda m3. And of course, lambda would be the parameter. Okay, so this is the parametric equations. All right. And now we look at a question. So what are the parametric equations of this line? So the first thing that we'll do is, of course, write down a line. Then let r be equal to x, y, z. And then we basically equate the corresponding components. So it's very, very simple. So here, what we're going to do is just say 2 plus lambda multiplied by 1 is going to just be lambda. 4 plus, oh, sorry, this would be minus now. So we have minus 2 lambda. So this would be 4 minus 2 lambda. And this would be 6 plus 3 lambda. Okay, so this is where lambda is elements of the real number set. So when we equate these, we'll get x is equal to 2 plus lambda, y is equal to 4 minus 2 lambda, and z is equal to 6 plus 3 lambda. And these are the parametric equations, right? Now the final form is the Cartesian equation. So if we consider the parametric equations, as we found before from the vector, we can get the Cartesian equations from this by solving for lambda for each equation and then equating them. So notice how we derive in them, right? So we have the parametrics, then we're going to solve for lambda for each equation, and then we equate them. Since this is all lambda, we can say that this is equal to this, which is equal to this. And this here is the Cartesian equation of a line. And note that a1, e2, e3 is a fixed point on that line, right? So let's look at the example, how we go through these three different forms. We have a vector equation in this form. Then we let r equal to x, y, z, and we simplify it to get the parametric equations. So when we get the parametric equations, we get to here, and then we go down by simplifying. And then we have x is equal to 1 plus 2 lambda, y is equal to 2 plus 3 lambda, and z is equal to 1 plus lambda. So we have these here. Now, obtaining the Cartesian equation, all we're doing again, like we did before, is we make lambda the subject to the formula. And since we have 3 lambdas, we can equate them. So we have x minus 1 over 2 is equal to y minus 2 over 3 is equal to z minus 1. And this is the Cartesian equation. So you see how we just went from all 3 going through like that. So yeah, that's how you do that example. So these 3 are the different forms of the equation of a line. And you see how we could go from one to the other very easily. Okay? Now we're going to look at parallel lines. Similarly to vectors, parallel lines are lines which are scalar multiples of each other. So we determine if lines are parallel by looking at their direction vectors. So we consider 2 lines in this example, r1 and r2. Okay, and we have, remember that these are the direction vectors, right? So we have 1, 2, and 1, and 2, 4, 2. Are these scalar multiples of each other? If yes, then they are parallel. If not, then they are not parallel. So 2 would be the scalar multiple. Therefore, these 2 lines are parallel to each other. So it's very similar to if vectors are parallel to each other. Are they scalar multiples? If yes, then they are parallel. If not, they're not parallel. Very simple. Now we can look at intersecting lines. To determine if 2 lines intersect, equate the equations of the lines, and if they are solutions to each line's parameters, then the lines intersect. So let's go through this. If we have 2 lines, r1 and r2, okay, where lambda and mu are the parameters, to be able to see if they intersect, there are a couple steps that we're going to go through. The first one we're going to do is to equate the equations. Then we're going to solve the system of equations for the parameters. So we're solving for lambda and for mu. And then we're going to substitute these values into the unused equation from the system. And if they are truly equal, then they do intersect. Now, to help you understand this properly, let's go through an example. Let's see if these 2 lines r1 and r2 intersect. So we're given r1 and r2. After simplifying them, we get 2 plus lambda, and then the second being lambda only because this is a 0. Then we get 1 plus lambda, right? And for r2, we get 3 plus 2 mu, 1 plus 2 mu, and then mu because this is a 0, okay? Then we're going to set the components equal to each other using the equality property. Remember how I told you that would come in useful. So we're going to let these equal to each other. So this would be equal to this equal to this, and this equal to this. And this would become our system of equations. So we have equation 1, 2, and 3. Then we're going to take two of them, all right? So let's substitute 3 into 2. Why did we choose 3? Because we already have a value for mu here. Mu is equal to 1 plus lambda. Ideally, you choose the simplest one because why would you not? Why would you want to make it difficult? What we're trying to do is solve for lambda and mu, but luckily we already have the equation transpose for mu. So what we're doing now is finding the value for lambda. Remember, all we want to do now is find the values for the parameters. In this case, mu and lambda. So what we're doing is substituting 3 into 2 to find lambda. Then we're simplifying to get lambda equal to minus 3. And then we're going to substitute lambda is equal to minus 3 into 3 to find the actual value of mu. Okay? So then we get mu is equal to 1 plus lambda. We know lambda to be minus 3. So mu is equal to minus 2, which is 1 minus 3. Right? So now that we have the values for mu and lambda, we have to substitute these values into the unused equation. So what is the unused equation? The unused equation in this case is 1, because remember we used these two already here. Okay? So we're going to substitute the values into the unused equation into the right-hand side and the left-hand side. And if these two sides are equal to each other, then they intersect. However, if they are not equal, the lines do not intersect, okay? So let's see, the left-hand side is 2 plus lambda. So 2 minus 3 is minus 1. And the right-hand side of this equation was 3 plus 2 mu. And we know mu to be minus 2. So we have 3 plus 2 multiplied by minus 2 is minus what? Minus 4, exactly. So 3 minus 4 is equal to minus 1. And is that equal to our left-hand side? Yes, it is. So we know that since the right-hand side is equal to the left-hand side, these two lines do in fact intersect. Okay, so that's how you find if lines intersect or not. And now we're going to learn about skew lines. So this is very simple because it incorporates the last two things that we've learned: if lines are parallel to each other or if they intersect. So skew lines are lines that are not parallel and they do not intersect. So if there is a question that asks if lines are skew or not, to be able to test it, or well, decide if they are skew, we have to do two tests. See if they are parallel and see if they intersect. And if both of these tests are negative, meaning that they are not parallel and they do not intersect, then, my friends, we have skew lines, and it's that simple. And the final section of this video will be about planes, and unfortunately not the aero kind. We're not going to learn how to become pilots. However, we will learn about the equation of a plane. Isn't that exciting? Okay, so there are two ways to find the equation of a plane. The first way is given a distance from the origin to the plane and a unit vector perpendicular to the plane. And the second way is given a point on the plane and a normal vector to the plane. So this is a vector perpendicular to the plane, right? So the first way, we can see that if we are given the distance from the origin to the plane and a unit vector perpendicular to the plane, this would be the formula. And the second way, you need to write these things down. You need to pause. Don't go as fast as me. The second way is equation of a plane given a point on the plane and a normal vector to the plane. This would now be the formula. All right, so let's look at the different forms of plane equations. We have the vector form and the Cartesian form. So let's suppose that A is a point on the plane and n1, n2, n3 is a normal to the plane with the unit vector. All right, so the vector form would be as such, or in this case, the second way. Remember, we have two equations, the first one here and the second one. And now we're writing it in vector form. This is how it would look. This is how they would look. And in Cartesian form, this is how it would look. All right, so these ways. Remember, when you consider the vector equation, you could derive the Cartesian form. So just take note of them now. And finally, we are going to learn about the cross product, which is important. So if we have two vectors, perhaps within a plane, and we would like to obtain the normal vector to the plane, then we can use the cross product. So pay attention now. Suppose we have A and B. We can calculate the cross product with the I, J, K unit vectors. So remember matrices. Remember, this is why I need to pay attention to things beforehand, okay? So I hope you remember matrices. If not, I hope you do. Either way, I'm going to teach you. So let's see. Recall the determinant of a 3x3 matrix. So to find the determinant of a 3x3 matrix, what we're going to do is we're going to start off with I first. So how we're going to derive all this, forget this part now, right? We're starting off here. So we have I, J, K, and then we're going to have, remember, we have A and B. So let's put A in first. So A would be A1, A2, A3. We're going to put it in this way, so horizontally. Then we're going to put B in horizontally as well, right? So we're starting off like that. Now remember, we have I, J, K. The first thing that we're going to do is write I, J, K. It will be positive, negative, positive. Then we're going to have to fill in these values here, okay? To get these values, what we're going to do for I, we're going to cross out the row and the column, and then whatever is left, we're going to write down here, okay? So we have A2, A3, B2, B3, and we're going to put them here, all right? Then we're going to do the exact same thing for J. Remember, this will be a minus sign in front of J, all right? So we're going to cross out the row and the column. So we're crossing out the row, column, and what is left? A1, B1, and A3, B3, okay? Same thing we're doing for K. Cross out the row, cross out the column. What are we left with? My bad. What are we left with? A1, B1, A2, B2. A1, B1, A2, B2. And from here, all we need to do is simplify the 2x2s. Okay, so this is a 2x2 here, right? So let's look at an example. If we want to find a vector perpendicular to 3i minus 2j plus k and I minus j, we calculate. So let's see. We're plugging in I, j, and k first. Remember that. The second thing we're going to do is plug in the first one. So we have 3i, so this would be 3 minus 2j, so it's a minus 2 here, and then we have k. So remember, if there's nothing in front of k, that means it's a 1. So we have 1. Then we're going to do the same thing for the second. So we have I minus j. So we have 1 minus 1, and this is 0 because we have no k value here. Okay? Then we're going to do the I first. Cross out the row and the column. This will be positive I. Remember, it's going to be positive, negative, positive. So for I, it's positive. Then we're going to put in the 2x2. Minus 2, 1, minus 1, 0. And we got this because we crossed those out and we left what was remaining. All right, the same thing. J would be negative. And we cross them out. And we get 3, 1, 1, 0. 3, 1, 1, 0. Lastly, for k, same thing, but this is positive. We cross it out and we get 3 minus 2, 1 minus 1. 3 minus 2, 1 minus 1. Now, all we have to do is simplify it. Okay, so recall for 2 by true matrices, if A is ABCD, then the determinant of A is AD minus BC. So for each and every one of these, we just have to do AD minus BC, AD minus BC, AD minus BC. And then, of course, this would be multiplied by these. Okay, so let's do it. We're simplifying all of these to get I multiplied by 1 minus j multiplied by minus 1 plus k multiplied by minus 1. So in the end, we get the vector perpendicular to both 3i minus 2j plus k and I minus j is I plus j minus k, and in component form 1, 1, minus 1. And that's how we find it. So that brings us to the end of today's video. I will be doing the past papers in the next video because this video is already very long. And I would rather not have you all lose your minds. So I hope you learned something, and thank you very much for watching.